Annenberg Media.
For most of human history, the power of civilization has been human power. H.G. Wells describes life during this period in his book Outline in History. Where a weight had to be lifted, men lifted it. Where a rock had to be quarried, men chipped it out. Where a field had to be plowed, men and oxen plowed it. The Roman equivalent of the steamship was the galley, with its banks of sweating rowers. For thousands of years, across cultures and continents, human survival and the advancement of society have depended on physical strength. In fact, it was not until the 18th century, about the time of the American Revolution, that a change began to take place. It's interesting that this change is also referred to by historians as a revolution, the Industrial Revolution. It began in England, where a series of simple mechanical inventions made it possible to harness the power of gravity and heat. At first, this power-driven machinery was too crude and inefficient to be of much use. But as the 19th century unfolded and mechanical technology improved, it became obvious that much of the work done by humans and their animals could be done faster, cheaper, and often better by machines. Human power, quote, was needed now only where choice and intelligence had to be exercised. The drudge, on whom all previous civilizations had rested, the creature of mere obedience, had become unnecessary to the welfare of mankind. Today, we've come to realize that our quality of life and our future existence on this planet depend on how we exercise this human power of choice and intelligence. During the last century, and largely as a result of the Industrial Revolution, much of the Earth's supply of geologic resources has been severely depleted by the almost insatiable appetite of our energy-hungry lifestyle and a growing population. In fact, most geologic fuels, including oil, natural gas, coal, and uranium, are considered to be non-renewable. Deposits of these materials form extremely slowly when compared to a human timescale. At present rates of consumption, we can expect that sometime in the next few generations, these materials will be unavailable or simply too costly to use. So at this critical time in our history, human power again becomes vitally important. Creative and enterprising scientists are using their knowledge and talents to search for new forms of energy. In the meantime, geologists are working to locate and to more efficiently develop existing sources of energy.
Of all Earth's geologic resources, none is more prized nor in shorter supply than oil. Oil may be found in ancient marine strata as much as 500 million years old. Along the margins of continents, the seas teem with microscopic life. As these organisms die and settle to the sea floor, they may be buried by sediment, which protects them from rapid decay. As this organic matter becomes more deeply buried, it is gradually transformed into oil and natural gas by heat and pressure. It typically takes millions of years for this to occur. Petroleum exploration requires locating the geologic structures that trap oil and gas. These structures are usually marked by changes in density underground. Geologists are able to detect these changes by bouncing seismic waves through Earth's crust.
And you have to keep in mind that down in the subsurface of the Earth, the rocks have different hardnesses. And when you have two formations or two rock layers that have a different hardness and they're in juxtaposition or in contact with each other, then you can get a reflection back. Just like looking into a mirror, you get a reflection of your face. Just like the sonogram reflects off of the baby's body and returns its image to the surface.
Seismic waves are artificially generated above potential oil-bearing rocks.
We have a truck called a vibroseis truck that actually shakes the ground. A vibroseis truck would shake the ground in an up and down fashion, much like a jackhammer on a construction site shakes the ground. We may drill a hole 5 foot or 200 foot down into the ground and load it with 5 to 20 pounds of dynamite and set the dynamite off, creating that shock wave that we need.
These shock waves are detected by electronic receivers known as geophones. The geophones are laid out in a line or grid pattern over the area to be mapped. The information recorded by the geophones is processed by a computer, which in turn generates a reflection seismogram.
You got about 30 seconds.
And what you see on this reflection seismogram is a series of reflections. And those are occurring where that source that goes down through the earth, that shock wave, bounces off of the subsurface rocks and comes back to the surface and is recorded at the geophones. So we see images of the subsurface.
Several seismograms are combined to produce maps showing the depths to oil-bearing formations.
Now that subsurface depth map would portray a structure in the subsurface, and that would be much like a topographic map portrays a mountain or a structure on the surface of the earth. So once we've done that, if we ascertain that there's a structure or a trap down there that has the capacity to hold hydrocarbons, and all the other things fit into the picture with respect to source, migration, timeliness, and reservoir rock, then we would make a determination of whether or not that prospect was economic. If it was economic and we were able to get the land, then we would possibly drill a well and hopefully have a large discovery.
Arco's site in Bakersfield, California, is thought to contain over 100 million barrels of oil in a deposit that is roughly 38 feet thick and 2,000 feet long. Although more than 1,000 wells have pierced this reservoir, a significant portion of the oil still remains underground.
The oil actually isn't contained in huge pools underneath the ground. Really, it's contained within these very small pore spaces of sedimentary rocks like sandstones and limestones. The flow openings through these rocks are really quite small, and it takes a tremendous amount of pressure to force the oil and gas through the pore spaces in the rocks.
In a new, untapped field, the natural pressure of the formation may be enough to drive the oil to the surface. But as wells draw oil from the ground, that pressure drops and extraction becomes more difficult. Typically, as much as 2/3 of the oil remains underground because of this drop in pressure. But a new technique called horizontal drilling is now being used to coax oil from partially depleted reserves.
The first step in perforating a horizontal well is to run long pieces of pipe called perforating guns into the well. These perforating guns contain jet charges that will blow holes in the pipe. The guns are run into the well on the end of well tubing, and once they're properly positioned across from the formations that we want to perforate, they're detonated by using water pressure in the well to ignite a firing head that starts the firing chain all the way down the guns. The guns fire over a 1,300-foot interval in a split second.
Horizontal drilling techniques allow engineers to penetrate shallow deposits that would have been too expensive to tap using vertical methods. This lone horizontal drill rig has produced approximately 900 barrels per day for the last 7 months. To achieve the same production rate with conventional drilling techniques would require 4 times as many wells at a 40% increase in cost.
Horizontal drilling is going to be used more and more in the future to try to get the last bit out of a lot of oil fields. In fact, some people estimate that within 10 years, about a third of the wells that are drilled are going to be horizontal. As the technology improves, the cost of the horizontal drilling is going to become more competitive with the conventional vertical wells also. And ultimately, I think it's going to make a big contribution to the recovery of oil throughout the world.
While the potential of horizontal drilling remains promising, scientists have adopted ever more exotic techniques in the quest for geologic resources. Through a process known as remote sensing, satellites circling high above Earth gather data from large areas of the planet's surface.
This is, of course, in contrast to the way we did it before, which is a person would map a little postage stamp area here and then another area over here, and then some bold soul would come and collect all these postage stamps of information and draw lines between them and say, okay, this is the integrated map of Oklahoma or the United States. And in the very course of doing that connection between the postage stamps, we quite often would lose the kinds of information and the kinds of insights that we were really trying to gain by virtue of integrating or of compiling a large map of a large area. So what remote sensing has done, or satellite remote sensing particularly, has given us a chance to look at the interrelationship between widely separated features and see those in a way that we've not been able to see before.
Satellites detect these features by measuring the electromagnetic radiation emitted or reflected by Earth's surface. Electromagnetic radiation consists of a continuous spectrum of energy. Visible light comprises one small part of this spectrum, which also includes higher energy gamma rays, X-rays, and ultraviolet radiation. At the other end of the spectrum lie lower energy radio waves, microwaves, and infrared radiation. Human vision is restricted to bands of visible light. Satellites, however, can peer into the realm of the invisible and see the full range of the electromagnetic spectrum.
Another aspect of the value of the data are that you're recording data in discrete spectral bands. A lot of these bands we don't even see with our eyes. So what we have available to us then is information in areas that are beyond, spectrally beyond what we can see with our own sensors, our own eyes.
Along with their wide field of view, this ability of satellites to detect different wavelengths of light provides scientists with a unique perspective on our planet.
So we really were created to take advantage of that technology. And the idea was that the company would be multidisciplinary. That is, we'd have geologists and foresters and oceanographers and climatologists and physicists and so on and so forth. That idea has persisted. Almost from day one, an awful lot of our business came from geology, particularly geologic exploration. It's an area for which remote sensing is just perfectly suited. In geology, as you would expect, the bulk of our clients have been oil and gas exploration companies, mineral exploration companies, and people and groups who are involved in groundwater exploration.
Recently, a group of oil companies asked the Earth Satellite Corporation to investigate the potential for oil and gas reserves in Pakistan.
The idea was to get an integrated notion of oil and gas occurrence in Pakistan, of course with the hope of, one, finding extensions of things that were known, and two, hopefully finding areas that had potential that really had not been examined in any detail or drilled, for that matter.
The data gathered by satellite was beamed back to Earth as a stream of computerized information. It did not look like a picture of Pakistan upon its arrival.
Because we record all of the information as a bunch of numbers, we can then use those numbers and apply mathematical techniques to them which enhance the information or combine the information in different ways to get a product we want.
Do you reckon those are little field boundaries there? These little...
Different features on the Earth are sensitive to different portions of the electromagnetic spectrum. Therefore, if you were interested in vegetation, we would use a different band combination, or if you're interested in urban areas, we'd select the band combination based on that, whatever you want to get out of the imagery.
The 247 and just see that.
By creating a composite picture from individual images, the imaging team is able to see geologic features and regional relationships that were not apparent when the area was studied on a picture-by-picture basis. Producing a mosaic is a complex task. Colors and contrast must be matched to minimize the patchwork effect.
Once all that is done, we take that composite print, the mosaic itself of all the scenes, we copy those in a copy camera. And then we make a large print for the CART lab so that they can add annotation. Once the annotation is added, then we make a final print that has the legend and all the information that the geologist would like to overlay on that.
When geologists examined the features of Pakistan on a large scale, they were quite surprised.
There are a series of folds in Pakistan that look like, kind of the wrinkles under your eye after you've been up too long. And the conclusion was that these really marked areas where we had thicker sequences of sediment. That is, these were old basins. And what we concluded was that we were really looking at a rather complex margin of an old continent.
The fact that the mosaic revealed features and relationships that had not been detected from the analysis of single images or from field investigations prompted geologists to seek answers to questions that might never have been asked.
And as we delved into the literature, we found that there was good evidence that, in fact, the Indian plate itself had bumped into Eurasia up on the northwestern corner and then rotated counterclockwise. So insights like that become just absolutely invaluable in trying to unravel the deformational history that may bear on where hydrocarbons might be located today. We were able to come up with a number of other areas that have not been examined that look like they have very, very large potential.
Creative techniques like reflection seismology, horizontal drilling, and satellite remote sensing not only make the development of existing oil and gas reserves more efficient, they also allow geologists to search for new oil fields more effectively. But as powerful as these technologies are, they represent only a short-term solution to our energy problems. And regardless of how efficient our oil extraction capabilities become, the widespread use of petroleum and other fossil fuels will continue to aggravate a number of serious environmental and public health problems. The simple, inescapable fact is that the world's supply of petroleum is finite and non-renewable. The best estimate of global oil reserves indicates that we've already used about half of the world's commercially available oil. And oil that's now forming in sedimentary rocks won't be available for millions of years. It's safe to say that many of us living today will see an end to the widespread use of petroleum as a fuel for transportation and for generating electricity. Shrinking supplies, rising prices, and the environmental cost of using fossil fuels has prompted a search for other forms of energy. And here, human power has again responded to alter the course of our future by creating new machines and new technologies to capture the intensity of the sun, harness the force of the wind, and use the heat of the Earth's interior. These energy sources are fundamentally different from fossil fuels. They produce little or no pollution, and they are, for the most part, renewable. These sources of energy have the potential to play a vital role in our future for generations to come.
One alternative to fossil fuels, which has been in use for some time, is hydropower. Water rushing through passageways in dams spins enormous turbines, which generate electricity. A more recent development is the wind farm. Vast numbers of air turbines stretched across hillsides convert the force of the wind into electric power. Light from the sun is yet another alternative source of energy. With the use of photovoltaic cells, sunlight generates electricity. It is also used to heat water and buildings. Each of these alternatives to fossil fuels is driven by Earth's external heat engine, the energy of the sun transformed into wind, light, or running water. But Earth's internal heat engine can provide energy as well. Hot rock in the shallow crust has been tapped to produce geothermal power. In volcanic regions, geothermal energy is used to heat thousands of homes and places of work. More commonly, however, it is used to generate electricity.
Geothermal sites around the world, there's quite a few. There's 250 plants operating in 16 countries on 6 continents. So it's widespread. The first geothermal power plant that actually produced electricity, like we are here, was in 1904 in Larbadello, Italy. So it's an old technology that's been applied in a lot of other places. The United States, per se, did not start until recently with the increase in energy costs.
The geothermal energy contained in the upper 5 kilometers of Earth's crust is said to be 40 million times greater than the energy contained in oil and gas reserves. But only a small fraction of this energy can be exploited economically. One area that is being explored for its geothermal potential is the Imperial Valley of California.
The crust is normally relatively thick in most places, but in an area like this where we are today, it's thin. It's only about 18,000 feet. So we're very close to the liquid rock within the earth, and that heat is very close to the surface, and water in the ground contacts that magma, brings heat to the surface, and we can produce it. And it's in areas like this where you get geothermal energy where we can use it. If you drill deep enough anywhere in the world, you can get the heat, but here we can drill shallow and get the heat.
The magma beneath the Imperial Valley heats up groundwater, causing it to rise through the crust. As the groundwater reaches the surface, it can flash or instantaneously vaporize to steam. This steam is then used to drive turbines, which generate electricity. But the groundwater contains salts which corrode turbines and clog pipes. These dissolved salts, called brine, must first be removed to purify the steam.
As it enters the plant, it goes into a large separation vessel where we take steam off the top and brine off the bottom. This first steam comes off at about 110 to 120 pounds, and it will go to a high-pressure turbine. It will spin the turbine and make electricity. The brine that comes off the bottom of that vessel goes to another separation where more steam is removed down to almost atmospheric pressure like we breathe. That steam then goes into another part of a turbine, makes more electricity. It's then condensed and put back with the brine or put into a cooling tower to generate cooling for the condensers.
Sometimes artificial means are used to vaporize the groundwater.
This brine, as it exists in the ground, the pressure in the reservoir is not enough for the brine to flow to the surface. So what we do is after we drill a well, we will induce it to flow with nitrogen gas. We will pump gas into it, which will start it to boiling, to flashing, and on its own it will generate, much like a teapot, it'll start to boil, and if you get enough heat, it'll boil out the top. Well, these wells will generate their own steam and they'll produce to the surface.
Geothermal energy is a stable source of power with relatively low environmental impact.
Environmentally, geothermal is one of the most benign energy sources we have. The only two that might be better than that would be wind power and photovoltaic cells. The major shortcomings to geothermal is it has a high capital investment, so you have got to have a lot of capital to get started. That's probably one of the biggest drawbacks to it. The second drawback is that we're really limited. There are only finite areas that can be developed.
Only a few places have the proper combination of heat, geologic structure, and clean groundwater to produce geothermal energy. And since heat is replaced quite slowly in rocks, geothermal stations usually tap all useful energy within just a few decades. Individually, neither geothermal, hydro, wind, nor solar power can substitute for the world's supply of fossil fuels. But collectively, they can make a significant contribution to our energy requirements. And as the environmental costs of burning fossil fuels escalate and reserves dwindle, the need to continue developing new sources of energy becomes even greater.
As we approach the 21st century, the fact that Earth's geologic resources are in finite supply is a reality that affects us all. There are very real and very predictable limits to the resources available for our use. And the primary reason for these limits is not supply, it's demand. It took 4 million years for Earth's population to reach 2 billion. The third billion was added in just 30 years. And today, we are growing at almost 100 million people every single year. With a population and a demand for resources both exploding, we as individuals can no longer continue along a path of energy addiction and wastefulness. No longer can nations afford to take from the land while ignoring the consequences to neighboring nations and to the other forms of life with which we share this planet. And no longer can the world community afford to only view Earth through the myopic eyes of competing self-interest. We need to adopt a global view, both in our technology and our philosophy.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.